Before we go any further, at this moment in our journey, what is the picture of an atom? How does an atom look like? I hope you haven't forgotten the model proposed by Ernest Rutherford. What emerged from the Rutherford experiment was a model that in many ways resembles the solar system. The positively charged nucleus and the negatively charged electrons attract each other. Again, the electrons must be in motion, otherwise they would collapse into the nucleus. When compared to the actual solar system, the atomic model has a jarring difference. The sun and planets are neutral, whereas the nucleus and the electrons are electrically charged. According to classical physics, when a charged particle, an electron in this case, accelerates, it should emit electromagnetic radiation, thereby constantly losing energy. Thus, when an electron moves around the nucleus, it should lose energy and eventually spiral into the nucleus, which means a planetary model of an atom should not be feasible, it should not exist. Further, the model didn't account for the stability of an atom. For a brief moment, let us recall the timeline of the events until now. Now being 1913. We start with Democritus way back in time, and the next major breakthrough comes with Thomson's experiment and the oil drop experiment. While all this is happening, in 1900, Planck had his breakthrough only for Einstein to bolster Planck's arguments in favor of the particle nature of light, which was, until then, proven to be a wave. Suddenly, after Einstein's paper on photoelectric effect, we encounter that light or radiation has dual nature. And in 1913, Niels Henrik David Bohr, a Danish physicist, took a leaf out of the idea of quantization and combined it with the Rutherford model to develop a quantum model for the hydrogen atom. He was the first person to formally use the idea of quantization to explain the nature of matter. Until then, the idea was only used in the context of radiation or light, but never for matter. Let us take a look at Bohr's postulates and see what makes it so successful. What are the assumptions involved therein? Take a look at this visual. As you can see, an electron inside an atom can exist only in certain discrete energy levels, E1, E2, and so on. The electron moves around the nucleus in a circular path or orbit. Bohr referred to these orbits as stationary states. An electron moving in a stationary state does not emit electromagnetic radiation. It does not dissipate energy in the form of radiation. Radiation is emitted or absorbed only when an electron jumps from one level to another. As you can see, there are infinite number of energy levels, but here we have only shown a few. The farther away from the nucleus, the higher the energy of the orbit. The energy of the photon, which is E photon, equals h nu, which is equal to the difference between the energy of the final state minus the energy of the initial state. So, when an electron moves from a lower energy to a higher energy level, it absorbs radiation. On the other hand, when it falls from a higher energy level to a lower energy level, the electron emits a photon with energy equal to h nu. In either case, the energy of the photon is the difference between the two energy levels. Lastly, there were certain limitations of angular momentum, requiring energy levels to have this form. The parameter n can take values like 1, 2, 3, and so on. These integral values are called principal quantum numbers. For n equals 1, the lone electron of the hydrogen atom is in its lowest energy state or energy level, which is said to be the ground state. Now, don't bother about the negative sign for the energy, value or function. It is a matter of convention and a bit of physics. The negative sign simply implies or means that the energy of the electron bound to the nucleus is lower than it would be if the electron were at an infinite distance where n equals infinity. At infinite distance from the nucleus, there is no interaction between the nucleus and the electron, and hence the energy is zero. Using these assumptions, which are called postulates, Bohr deduced the radius of each stationary state or orbit and also gave an expression for the speed of the revolving electron in that particular orbit. We'll take a look at the formal derivation for the expressions of energy, radius as well as velocity in a separate video, but for now, make a note of these expressions. The parameter n here is the principal quantum number. The current model of an atom has nothing whatsoever to do with this Bohr's model. In other words, this is not what an atom looks like, but Bohr's model was a historic step in the right direction. It could explain the atomic structure of one electron systems with very reasonable success, and the model was nearly an exact fit with the experimental data or results from spectroscopy. A number of possible energy transitions in the Bohr model are shown here. Of these transitions, the Balmer series corresponds to the visible range. Another important reason why Bohr model is noteworthy is because it was the earliest to imbibe the idea of quantization. Before we wrap up this video, let us take a look at some of the reasons why the Bohr model did not succeed for the overall nature of atom. The Bohr model worked very well for single electron species like hydrogen, but it couldn't explain the spectroscopic results of multi-electron species. As sophisticated spectroscopic instruments and techniques were developed, some spectral lines were seen to be split into finer lines. In other words, the Bohr model failed to explain finer details. Further, Bohr's theory was also unable to explain the splitting of spectral lines in the presence of magnetic field, which is sometimes referred to as Zeeman effect, or the electric field. The splitting there would be referred to as the Stark effect. There is also a fundamental flaw in the Bohr model, which was discovered by Werner Heisenberg some 14 years after the model was introduced. Heisenberg showed that it is not possible to simultaneously know the electron's orbit radius and its momentum, as Bohr had assumed it was possible. Lastly, the Bohr model could not explain the ability of atoms to form molecules by forming chemical bonds. In this video, let us briefly take a look at the postulates of Bohr's atomic model for a single electron species like the hydrogen atom. So let us take a look at the postulates first. Bohr postulated or proposed that nucleus is at the center, and of course that was already known from the Rutherford's experiment. Electrons revolve around the nucleus in circular orbits. Moving in a circular orbit or moving in a circle, it implies that the electrons are constantly changing direction. When they constantly change direction, you will learn in physics that though they may be traveling the same speed, for instance, say the electron is moving at 80% of the speed of light, okay, 0.8 c, may that be the velocity of an electron. So if it is going, may that be the speed of the electron. At that constant speed, if it is going in circle, obviously if it is going in circle, it is going to be constantly changing directions. When that happens, Though the electron might be traveling at a constant speed, it will have a different velocity. Now why is this? Because speed is a scalar. It doesn't have any direction associated with it. But vectors, they have both a value as well as a direction. So velocity not only has a value, it also has a direction. And when the direction keeps changing, it means that the velocity keeps changing. And when velocity keeps changing, we term this to be acceleration. So moving in a circle implies acceleration, and the electromagnetic theory, which was given by Maxwell and many others, which was improved upon by many other scientists, it doesn't matter who gave the theory, but it states that when a charge is accelerating, it will emit electromagnetic radiation in the form of energy. So energy in the form of electromagnetic radiation rather. So when it is constantly emitting energy, so it is going to be losing energy, isn't it? Energy has to be conserved. So when it is losing energy, then very tricky things happen. Suppose we have an electron having moving in a circular orbit at a constant speed at say a distance r. So according to the atomic theory given by Bohr, it is supposed to have a particular kind of energy, a particular amount of energy in that circular or stationary orbit. Bohr called these circular orbits as stationary orbits. Let me tell you why. But when the electron is moving and it is having a particular kind of energy, the classical theory of electromagnetic waves or light waves, it predicted that when a charge accelerates, as in exactly in our case, that is exactly what is happening, as in a charge is accelerating even though it is moving at a constant speed at a particular distance from the nucleus. When this happens, it is going to emit radiation, and when it emits radiation, it loses energy, and hence the classical theory suggested that the electron should spiral and crash into the nucleus and disappear, as in an atom was supposed to collapse. But according to Bohr's postulate, he said that there are specific orbits, circular orbits, which he termed as stationary states, in which if the electron is revolving around the nucleus, there won't be a decay or dissipation of energy. So Bohr assumed zero losses in these stationary states, which were a fancy word for circular orbits. Now I think the word stationary might mean something, because since there is no loss of energy, the electron can stay put. It can be at that particular distance from the nucleus without losing energy, and for this reason, coupled with the fact that the energy of that particular orbit or stationary state is going to remain constant, Bohr termed the whole thing as the circular orbit as a stationary state. When the electron transits, when I said electrons, don't go by the word electrons. Bohr's model holds only for species like the hydrogen atom, as in species which have just the one electron. So it is only valid for single electron species. One of the most important shortcomings of Bohr's model is that it couldn't explain multi-electron systems, not even helium, which has one more electron than what a hydrogen atom has. So when electron transits between these stationary states of a single electron atom or single electron species, it absorbs or emits energy in the form of electromagnetic radiation. By convention, by practice, from electricity or electrostatics rather, we assume that the energy of the system, as in the energy of the atom, to be zero when the distance between the nucleus and the electron is infinity. In other words, when the electron is at an infinite distance from the nucleus, or we can say that the electron is at a very large distance from the nucleus, it is assumed to have zero energy. As we move away from the nucleus, the energy associated with the stationary state increases. So according to Bohr's model, there are only fixed orbits that an electron can revolve around in, and these are called stationary states. The closer the stationary state is to the nucleus, the lower the energy. But by convention, at the greatest distance or at infinity, the energy is zero, which means that the closest energy state or stationary state the stationary state which is closest to the nucleus should have a negative energy. So this might seem a bit counterintuitive and contradictory, as in how can energy be negative? We are not saying that energy is negative. We are just taking the energy assumed by the system when the electron is at an infinite distance to be zero. And we know from electrostatics, from physics, from electricity and magnetism rather, that the closer the stationary state is to the nucleus, the lower the energy. So as the stationary states, as the radius keeps increasing, the energy of that particular stationary state 1, 2, 3 and so on. So the farthest energy state will have the highest energy, but highest energy is zero. So everything else is going to be lesser than that. Is it not? Yeah. That is a very important concept to grasp. So the difference in energy observed when the frequency of energy absorbed or emitted is given by the Bohr frequency rule, which states that, see, electron is present in one energy state or one stationary state. It transits to another. So either it has to absorb or emit a radiation, a photon. It has to either absorb or emit energy, is it not? So del E is nothing but E2 minus E1. Since we don't know whether E2 or E1 is, which of the two is greater, we don't bother about that. So we just take the absolute value. We only take the quantity or the magnitude. So it could be minus 4 or plus 4. We don't know which is it. So we just take it to be 4 to make the calculation simple, and so that we can ascribe some sense to it. So we also know that E equals h nu. So this shift or difference in energy, del E by h, should give you the photon of the radiation, frequency of the photon of the radiation which is absorbed or emitted. So nu is given by del E by h, which is nothing but a modulus of E2 minus E1, as in we are taking only the positive quantity. We are only taking the magnitude of that difference, E2 minus E1, the whole thing divided by h. Angular momentum of a stationary state n is given by a formula which you will later study in physics. The angular momentum is the rate with which an angular sweep is happening and so on. Right now I'm not going to go into the physics, but for the time being it suffices to say that you need to keep this relationship in mind. I'm talking about this equation. mvr gives the angular momentum, and Bohr postulated, he suggested that it has to be quantized. When I say quantized, it cannot take a continuous value. There are only so many things that it can take. And when I use the word quantized, I'm trying to drive the idea that mvr, which is nothing but the angular momentum of the stationary state, is an integral multiple of the quantity h by 2 pi. H is Planck's constant. So here nh by 2 pi is equal to mass of an electron times velocity of an electron times radius, mvr, which is the angular momentum of that stationary state. N can take values, positive integer values like 1, 2, 3 and so on. So Bohr, for whatever reasons, he just assumed that, he postulated that this angular momentum mvr has to be a constant integral multiple of h by 2 pi, where n is the principal quantum number, and as n varies, n is 1 is one stationary state, n is 2 is another stationary state and so on. So Bohr's theory helps us predict radius. It also quantifies the velocity of the electron in that radius or stationary state, and also Bohr's calculations, or Bohr's theory rather, it gives us the energy of that particular stationary state. Let us take a look at how to go about deriving these things. As a word of warning, I'm going to use a lot of physics that I'm pretty sure many of you might not have come across. For instance, I'm going to use a little bit of electrostatics, and also I'm going to use something called centripetal force. For the time being, I'm not going to explore these concepts in great detail because I'm not here to teach you physics, although I love the subject. but it would be too long a video if I have to teach you random stuff from say 11th standard, 12th standard and so on. So for the time being, let us just stick to the concepts based on faith, good faith rather. Yeah. So suppose a particle is moving around a center. You have a center and there is a particle moving around it, or there is a particle and moving, another particle is, there is a center and another particle is moving around it. So it is constantly moving, right? What you can think of is you take a thread, one end of the thread you hold it between your fingers or in your hand, and on the other end of the thread you tie a small piece of stone, tie it rather really well, and if you actually give it a whirl, if you constantly try to rotate it, swerve it around, so you will see that if you do this, you will be able to see that the thread is getting the stone or whatever mass is at the other end to actually move around in a circle. What you can do is you can tie it in a long pole, tie the loose end of the string in a long pole, and you can actually do this with you can actually whirl it around. Then you will actually be able to produce a very symmetrical circular motion. It is going to be near symmetrical. It is not perfectly symmetrical because there are many forces at play, but we can assume that it is actually moving around in a circle. So the tension in the string is what is pulling the mass towards the center. So there is a force on that string, and that force is something that we call tension, and this force is the centripetal force which gets the mass m to move in a circle. That is called a centrifugal force. Sometimes it's called centripetal force. So the value of that force is going to be me times v squared by r. So me is the mass of whatever is moving around in a circle, v is its velocity, and r is its radius. So that is centrifugal force. We've already seen not v as in, so I think you might be familiar with the gravitational force. There are two masses, m1 and m2. So the gravitational attraction that one mass feels because of the other is going to be proportional to the product of the masses, and it varies inversely as the square of the distance between them. So we have the force, gravitational force, experienced by either, because they are action-reaction pair. The force on m1 will be equal and opposite to the force on m2. But the magnitude of the force is going to be the same, as in it is given by g/mm by r square. Likewise, similarly, we have something from electrostatics. When there are two charges q1 and q2 separated by a distance r, the force that either of the charges experiences because of the other is going to be directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Proportionality constant is 1 by 4 pi epsilon naught. It is a term which keeps appearing again and again and again whenever electrostatics is involved. So that is the force. So I'm just saying, I'm asking you to accept on good faith that this is the proportionality constant and this is the force. Z is the atomic number. So we are just assuming that there is a one electron system, but we didn't say that it has only one proton, as in we are not saying that it is going to be just the hydrogen atom. It could be Li2 plus and so on. So if you look at Li2 plus, it has just the one electron but more than one protons in the nucleus. So Z is going to be the atomic number, which in other words is going to give us the number of protons. Let us assume that E is the charge of an electron. A proton will also have an equal and opposite charge. So the force between two charges is going to be ZE into E. So the product of the charges, that is going to be ZE into E or ZE square. And the distance between them is R, like I said. So there is a nucleus and an electron is going around and around and around. And that centrifugal force is given by this formula. Also, because there are two charges, they experience electrostatic force. It could be attractive or repulsive. If they are opposite charges, they attract. If they are like charges, they repel. But here it is going to be an attractive force because proton and electrons, they share an opposite charge. So this centrifugal force is going to be equal to the electrostatic force. Why is this the case? It is because of the electrostatic force. The electrostatic force is the centrifugal force, which is causing the electron to move around the nucleus in a circle. So we are equating these two and we are getting an expression for velocity squared as z e squared by 4 pi epsilon naught MER. Now I admit this term here is pretty complex, it sounds pretty ominous, but this is an important derivation. So you may not understand terms like centrifugal force or electrostatic force. For the time being, make a note of them, write them down, practice and commit them to memory, internalize them. Just like Planck's idea of quantization, Bohr assumed that the angular momentum is quantized. It was an inspired, a very inspired move. Planck, in his explanation for black body radiation, he assumed that energy is quantized, and for whatever reasons, of all the quantities in the world, for reasons unknown, for reasons that I cannot come to terms, Bohr assumed that angular momentum is quantized. mvr equals nh by 2 pi. Now this will also give you a term for velocity in terms of, see, you have mvr v here, okay, so v will be nh by 2 pi times 1 by mr, right? So yeah, so nh by 2 pi mass of an electron times r. So nh is on the numerator, 2 pi mer is on the denominator. So we square these. We already got an expression for velocity squared in the previous page. So I've kept it as equation number 3. So equation number 3 and equation number 4 both are giving us different expressions for velocity squared, which means we can equate 3 and 4, which is exactly what we do, and this will give us the radius of a particular stationary state. Remember, I told you that electrons can only revolve around the nucleus in fixed radii, and these orbits, these circular orbits, the path that the electrons take, they are called stationary states. So we have found an expression for the radius of a particular stationary state, r as a function of principal quantum number n and z. All the others, if you look at them, they are constants. So if you plug in the values of epsilon naught, which is the constant from electrostatics, we know the value of h to be Planck's constant, we know what is pi, we know what is the mass of an electron. We plug in these values and we get r equals n squared by z into 52.9 picometers. So this gives us the value for radius. So we have already obtained an expression for velocity. Velocity equals nh by 2 pi mer, and we also know what the radius is. So we just plug in the values and we get an expression for velocity. So earlier we got an expression for radius, now we have an expression for velocity. So as you can see, it is directly proportional to z and inversely proportional to n. Everything else is a constant in that expression. Now let us derive an expression for the energy. A hydrogen atom or a one electron species has an electrical configuration. It has some protons inside the nucleus, it has an electron revolving around. Do observe, it has only one electron, always keep this in mind. So total energy is going to be a function of the kinetic energy and the potential energy, which is because of the electrical configuration of the system. So many of you might have some idea about gravitational potential energy, right? So we take, suppose in this height, we take the potential energy to be 0 and we lift a mass of m and put it here. So the difference in these two states is going to be a height of h, and it is radially outward from the center of the earth. So the potential energy, if we assume the lower energy to be 0, then the higher energy is going to be mgh. So something similar goes on here in terms of the electrical configuration of the system. So we already know, we have a reasonably good idea of the kinetic energy because we know what the mass of an electron is, we know its velocity. Just now, some time back, we obtained an expression. I'm talking about this expression for the velocity of an electron in a particular orbit or a stationary state. So we already know what kinetic energy is. Now we need to do something to derive the value of the potential energy. And I'm warning you that this is going to involve a lot of physics that you haven't yet learned, but bear with me and commit these things to memory, because this is a very oft repeated question. This is a very important area in terms of your examinations, and people try to test your concepts here. And I don't know if this is a consolation. If it is any consolation, you will study Bohr's model. You might study Bohr's model later in class 12 as part of your physics curriculum. So let us get on with deriving an expression for the potential energy. Coulombic force, that is electrostatic force, is 1 by 4 pi epsilon naught Z square by R. Here I have used a minus because it is an attractive force. We are playing with vectors and we are going to use a bit of calculus, which I admit is far stretched right now, but there is no other choice. So work done is F vector dot dr vector. That is also something that you will learn in work, power and energy in physics, maybe even in Newton's laws. So we have this expression. So this is the force, and dr is the small displacement which is resulting because of that force. And if you look at the force, this is a function of the radius. Everything else is a constant. So the force itself is a function of the radius, and at a particular distance r, we have the electron, and the Coulombic force or the electrostatic force is causing the electron to move a little bit. And so that is the energy. So that displacement and the force, and we couple these two factors and try to get us F vector dot dr vector to get us the work done. So potential energy is nothing but work done in moving the electron from infinity, that is r is equal to infinity, to a point at a distance r from the nucleus. So from infinite distance, we are slowly moving this electron by very small, tiny, infinitesimal distances. And we are trying to calculate the total work done in doing this. When I say this, I am saying that we are moving the electron from distance r equals infinity to a distance r equals r. So from infinite distance, after we push it in very slow installments, infinitely many such installments, final resting place or final position of the electron is at a distance r. Earlier it was r equals infinity. So we use a bit of fancy calculus, we use integral calculus, we integrate dw, which is nothing but F vector dot dr vector. We know what is F, and that is what we have here, and we get this expression for the potential energy. You have to remember this when you study electrostatics as part of your curriculum in physics. You will definitely understand this. For the time being, please commit them to your memory. So total energy is nothing but kinetic energy plus potential energy. Kinetic energy we already know, potential energy we just derived. So a different aspect of deriving kinetic energy, we could actually do that. We already know that centrifugal force mv square by r equals Coulombic force Z square by 4 pi epsilon naught r square. So from there we can actually derive an expression for half mv square, or you can use the expression for velocity, square it and multiply it with half, and multiply the obtained product with the mass of an electron to get half mv square. Either way, we get the kinetic energy as this Z square by 4 pi epsilon naught r. And we also know the potential energy, which is nothing but negative Z square by 4 pi epsilon naught r. There must be a small mistake here. This is going to be 8. Check it out. I missed out the half. This half is what I have missed, but now I have taken that into account. So kinetic energy plus potential energy is what we have, and so we get the E total. So this is the expression for E total. I'm talking about this expression, minus Z square mass of an electron into E power 4, the whole thing divided by 8n square and it's 8 n square h square epsilon naught square. So epsilon naught is a constant from electrostatics. It is called the permittivity of free space. Mass of an electron is me. N is the quantum number n, which can vary from 1, 2, 3 and 4. So this is the expression for energy, and it is a function of z square as well as n square, but z is going to be constant for a given atom because we know it only has that many protons, and this is something that we already know. So if you look at this expression, E is the charge of an electron, me is the mass of an electron, z is the number of protons inside of the nucleus, or z is the atomic number, 8 is a constant, h is a constant, epsilon naught is a constant. Is it not? N can vary 1, 2, 3 and so on. So n equals 1 has that much energy, n equals 2 has that much energy, and electrons can exist only in these states where n equals 1, 2, 3, and if we plug in the values for n equals 1, 2, 3, 4 so on, in this we get very distinct states of energy. So this is what is given by the Bohr's theory. So this is the final formula for total energy. So you have to keep the radius in mind, the velocity in mind, the total energy in mind, and never forget to remember the kinetic energy separately as well as the potential energy separately. If anything, one is a constant times the other, find out which is which. So that is so we have come to the conclusion of the derivation for velocity, radius, kinetic energy, potential energy and total energy. All of these as a function of n and sometimes z, but do observe that for a given atom z is going to be constant. So all these things are velocity, kinetic energy, potential energy, total energy, they are all functions of the principal quantum number n. So if you want to calculate, if you just plug in the values of all the constants, so E of n, the energy of any stationary state is going to be minus 2.18 into 10 power minus 18 into z squared by n squared joules. Z is the atomic number of the given atom. So this is going to be the energy, the total energy, minus 13.6 z square by n square electron volts. So there are two different units here. One is the joule and the other is the electron volt. So in both cases we have given you the values, and you have to remember these values. And like I told you earlier, as n increases, as in n equals 1 is the closest energy state to the nucleus, n equals 2 is farther, n equals 3 is farther and so on, n equals infinity is going to be the farthest. That is where at n equals infinity the electron has zero energy, and n equals 1 is negative, 2 is slightly less negative, 3 is even more less negative and so on and so forth. But how do we observe this as a mathematical pattern? So as n increases, the distance of the electron or the distance of the energy state from the nucleus, that is also going to increase. But here we have E of n as a function of z square by n square. Z is a constant, forget about that. So now as n increases, 1 by n square, n is a positive integer, so as n increases 1 by n is going to decrease. 1 by n on 1 by n square, the 1 by n square is also going to decrease because n square is going to be even bigger than n, correct? Since the whole of 1 by n square is decreasing, the negative of that is going to increase, is it not? Correct? So think of it like this, 5, 4, 3, 2 and 1, it is decreasing. But if you put a negative value there, it is going to increase. Negative 5 is lesser than negative 4. Negative 4 is further lesser than negative 3. Negative 3 is smaller than negative 2. Negative 2 is smaller than negative 1, which is again smaller than 0 and so on. So that is a very simple mathematical way to look at the energy. So when an electron moves from a stationary state n2 to n1, the energy change is given by del E equals E2 minus E1, correct? So if you plug the values of energy obtained from the previous state, then we are going to get a formula for this del E as this in terms of joules. Now if you divide this by 1.602 into 10 power minus 19, that will give you the del E in terms of electron volts. But this will be the energy of the photon emitted or absorbed. So from a lower energy to higher energy, if the electron is moving, it is going to absorb an energy, and from a higher energy, if it is going to fall to a lower energy state, it is going to emit radiation or emit photons. So this change, this difference in energy states, that is given by this formula. This you can verify. Take a piece of pen and paper, write these things down, practice them, commit them to memory and internalize them. But del E from Planck's equation is equal to h nu of the photon. See, when it is making the transition, it is going to either absorb or emit a radiation, right? And that is going to have h nu as its energy. So this is the energy, and we can actually find out the value for nu. So nu will be, it's a very complicated seeming formula, but when we plug in the values, it whittles down to 3.29 into 10 power 15 z squared hertz, and this is multiplied by 1 by n1 squared minus 1 by n2 squared. So that is the formula for the frequency. And frequency is nothing but c by lambda, or the speed of the wave by its wavelength. So c by lambda is 3.29 into 10 power 15 into 1 by n1 squared minus 1 by n2 squared into z squared hertz, or you can keep 1 by lambda on one side and take c to the other side and divide it as part of the denominator. So this will give you the Rydberg formula, which the Swedish scientist Rydberg derived as an empirical result. He just gave this formula without any mathematical basis. Bohr went one step further, in fact several steps further, and he gave a very established formula. So 1 by lambda is the wave number, and this is the formula for the wave number for such a transition. And that concludes this problem. Now let us take a problem which is based on Bohr's theory or even the Rydberg formula. It goes like this: calculate the wave number for the shortest wavelength transition in the Bohr series of atomic hydrogen. So we need to calculate the wave number, and we are given that we have to do it for the shortest wavelength transition in the Bohr series of atomic hydrogen, which is the one electron species. How do we go about this? So we need the formula for wave number, which we derived some time back as part of the Bohr's theory, and they are talking about the shortest wavelength. E equals h nu is Planck's formula, and E equals h nu, nu equals c by lambda, so E equals hc by lambda. Okay, we need the shortest wavelength. Now try and correlate the formula for the energy, as in E equals hc by lambda. So if you look at that formula, we have h and c, which are both constants in the numerator, and in the denominator we have wavelength lambda. So energy is inversely proportional to lambda. So they want the shortest wavelength transition in the Bohr series. So in other words, they are looking for the highest energy, the transition where the transition which corresponds to highest change in energy. So that is what we need to compute or calculate. So from spectroscopy, so you might have looked at the visual in the other videos, in our other videos, where electrons are transiting from different stationary states. For instance, so there is a nucleus, and in the closest state, for n equals 1 is the ground state, or the closest energy state, which is the stationary state which is closest to the nucleus. N equals 2 is farther, 3 is even more farther, and so on and so forth. N can take only 1, 2, 3, 4 and so on, all positive integer values. It cannot have fractional values, irrational values and so on. It can only take positive integers as values. So for n equals 1, that particular stationary state, which we also sometimes refer to as the ground state because it has the lowest energy, that state n equals 1. So any transition to or from n equals 1, that is the Lyman series. So that is what we have actually written here. So see, you have, let me just redraw that. You have the nucleus and you have different states. So this is n equals 1, this is n equals 2, this is n equals 3, and so on. So when the electron is in state 1 and it transits, it cannot fall any lower than that, because that is a stationary state corresponding to the lowest energy, and n can take only the smallest value that n can take is 1. So it can transit to 2 or to 3 or to 4 or to any other stationary state. Such transitions where electrons either fall to n equals 1 or from n equals 1 they transit to other states. Such transitions, they come under the Lyman series. For Ni, I am using the subscript I to denote I as in I for interest. Interest as in we are interested in that particular stationary state. So Ni is the stationary state in which we are interested in. So if Ni equals 1, then it is Lyman series. For n equals 2, what are the transitions possible? It can transit back to n equals 1, but that would correspond to Lyman series, so we are not interested in that. So from n equals 2 to 3 or 2 to 4, 2 to 5, 2 to 279, 2 to 109,677, whatever, any positive integer. From 2, the electron transits, or from other, for other stationary states, from other stationary states, if the transition happens to 2, then it belongs to Bohr series. The exception that there is a transition between 1 and 2, that is going to be part of Lyman series, so let us not worry about that. So now we know Bohr series, and likewise this can go on. For Ni equals 3, we have the Paschen series. For Ni equals 4, we have the bracket series. For Ni equals 5, we have the Fund series, and so on. Probably Ni equals 6 gives us the Humphrey series, but yeah, Lyman, Bohr, Paschen, bracket, Fund, and Humphrey, which I haven't written it down, but these are the most important ones. So we are, if you go back to the question is for the Bohr series, is it not? We are looking at Bohr series. So Bohr series is Ni equals 2. So we are looking at a transition where the electron is in n equals 2. Electron is in a stationary state or orbit corresponding to n equals 2. Sometimes this is also referred to as shell. For shell n equals 2, the electron is there. And we are looking for a transition which has the maximum energy or the least wavelength. And obviously the transition cannot be n equals between 2 and 1, there is no transition. So since we are talking only about Bohr series, 2 to 3, 2 to 4, 2 to 5, and so on and so forth. Such transitions is what we are talking about. And we know that E equals hc by lambda. So E is inversely proportional to lambda, which means shortest wavelength corresponds to the highest energy. The electron has the highest energy at infinity, is it not? So we are interested in the highest del E or the smallest lambda. So when there is a transition, there is going to be a change in energy which is equal to the difference between the energy states. But the highest energy shift or highest del E is going to be when the electron transits between n equals 2 and n equals infinity. So that is going to be the largest energy gap, is it not? So we are looking at a transition between n equals to 2 and n equals infinity, or n to n infinity. We just have to plug in the values, that's all there is. So we know the formula for wave number. It is a Rydberg formula. 109677 per centimeter is the Rydberg constant. Z square, here Z is the atomic number, and atomic number for hydrogen atom is 1, and we know what is N1 and what is N2. So for Bohr series, so this value is going to be 2. And thus we plug in the values and we compute, and it comes out to be 27419.25 per centimeter, or approximately 27419 waves within a centimeter, or that many wavelengths. When I say waves, you can also think of it as that many wavelengths. So we have that many waves per centimeter, 27419 waves per centimeter. So wave number is what we set out to calculate, and that is what we have done. And that concludes this problem. Let us take another very interesting problem. This is also based on Bohr's model. The wavelength corresponding to maximum energy for hydrogen is 91.2 nanometers. Find the corresponding wavelength for He plus ion. So I'll read the question again. This seems very small, but it is equally cryptic. The smaller, the more cryptic. That is how it seems to me. The wavelength corresponding to maximum energy for hydrogen is 91.2 nm. They are saying maximum energy, which means it should be the shortest wavelength, right? Find the corresponding wavelength for He ion. So how do we approach this problem? They have given that del E is maximum or lambda is the least possible. They are asking us to compare. They have given that particular wavelength, the lambda smallest or del E highest, the wavelength corresponding to del E highest to be del E, not del E, del E as in del E, change in energy, to be the wavelength corresponding to that to be 91.2 nanometers. Find the corresponding wavelength, as in now we want to find the wavelength for a helium ion. So what is the difference between a hydrogen atom and a helium ion? Obviously don't tell me that one is an atom, one is a neutral species and the other is ion. Here with respect to this particular problem, we are not interested in something so obvious and in your face. Both are one electron species, and most importantly helium has more protons than the hydrogen atom, is it not? The number of protons is going to be more. So definitely see, there are more protons in the nucleus, and there is just the one electron. Now tell me, will it going to take more energy to remove the electron from its from wherever it is? Basically, highest energy transition is going to be between the lowest and the highest energy states, correct? We want del E, the change. There is an electron, it is transiting between two states. Bohr's theory states that there are only fixed orbits, and these orbits have corresponding radii, wavelength, potential and kinetic energies, as well as total energies, En. En is nothing but minus 13.6 into z squared by n squared electron volts. Z is the atomic number, n is the quantum number corresponding to that particular stationary state. So all these things we know. Highest energy. So when will you have highest energy? When electron transits between the lowest energy level to the highest energy level, or vice versa, from the highest energy level to the lowest energy level. Either way, the photon, which is if it is going from lower to higher, it is going to absorb energy, so it is going to absorb a photon. If it falls or de-excites from a highest energy level, from the highest energy level to the lowest energy level, then it is going to emit radiation, is it not? So, and we are interested in the wavelength of this particular radiation. We are not interested particularly about the transition, as in which direction it happens. We don't care about that. We are only interested in the wavelength of it. Fine. So that much we know. Now, we require some energy to say transit the electron in a hydrogen atom from its lowest to highest. A helium ion, He plus ion, it has extra protons and the same amount of number of electrons. So it is going to be tougher, because we need to overcome a greater electrostatic force, a force of attraction. So it is going to take you more energy than what it would take for you to remove the electron from its lowest and put it in the highest for a hydrogen atom. In the case of a helium ion, it is going to be more energy, which means smaller wavelength. So definitely our answer should be much smaller than 91.2 nanometers. So this much is pretty obvious. Maximum energy corresponds to wavelength which we are interested in. So from the derivation, we know what wave number is, and we know the formula, the Rydberg formula, which Bohr actually derived mathematically. In that formula, we are interested in the highest energy transition. So when electron moves from the lowest orbit or lowest stationary state n equals 1 to n equals infinity, that is when it is going to happen. So take a look at this formula. Don't bother about the sign because this is more straightforward than what it looks like. So we have the wave number, or the reciprocal of lambda. So I'm using lambda subscript h for hydrogen and lambda subscript he for helium, which we will come to later. So 1 by lambda h equals RH, which is some constant, which could be Rydberg's constant, into which is Rydberg's constant. 109,677 per centimeter, that is what the value is it not? So RH times z square, the whole thing multiplied by 1 by ni squared minus 1 by n infinity squared. N infinity, where n is equal to infinity, 1 by n infinity will get cancelled out, as in this term will vanish. It will become 0 and we are left with this. As you can see, take a look at this. So this is directly related to this. So keep this as equation 1. Now do the same thing for helium. So we just need to know from the problem statement, we need to be able to decide exactly what formula we need to use. This comes with practice, but if you practice with the intention to be able to select the right form of the Rydberg equation, then it would simplify your calculations and save you a lot of precious time, especially in competitive exams. So we do the same thing with helium as well. 1 by lambda He equals RH. Here I didn't use RHE because that constant is Rydberg's constant. That H doesn't reflect a separate constant for hydrogen, a separate constant for Rydberg and all. From the equation, because we are taking z square and n square into account, here basically what I'm trying to say is that this H doesn't stand for hydrogen. RH is just a constant. It is going to be the same in both equations. So 1 by lambda He equals RH times z square into 1 by ni squared minus 1 by n infinity squared. So first state to infinity, once again 1 by lambda He is equal to RH into ZHE square. Here apparently I left out a subscript. So this is equation 2. Now lambda He by lambda H will be equal to ZH the whole squared by ZHE the whole squared. So it's going to be 1 by 4th of this thing, yeah. So atomic number of hydrogen is 1, atomic number of helium is 4. So lambda He by lambda H is equal to 1 by 4. So lambda He is lambda hydrogen's wavelength, wavelength which corresponds to the highest transition in energy, which is 91.2 nanometers divided by 4. So as predicted earlier, we are getting a smaller wavelength because it would take much more energy to remove electron from the lowest orbit, or the stationary state corresponding to the lowest energy, that is n equals 1. For helium, if you want to do it for helium, it would take more energy than it would take for hydrogen. And what are we doing? We have a nucleus, we have the electron in its lowest state, we are trying to remove it and put it into the highest state. And for this, what do we need to do? We need to supply energy in the form of photons or electromagnetic radiation or some form. It could be electrical energy, sometimes you could just heat it. It doesn't matter how this happens, but it does, irrespective of how it happens, energy absorbed is a photon, or energy emitted is also a photon, which have that characteristic frequency or wavelength or whatever we calculated. So that is something that you need to keep in mind. And that concludes this problem.